Good afternoon. Good night. Just regarding to where you are. And my name is Xinxin Xiao. I'm basically in the Technical University of Denmark. I would like to give the presentation of the recent work based on my PhD in Ireland with the supervision of Professor Adam Magner. And in 2018, I then moved to Denmark, starting to be a postdoc. So the talk today is about Dealloyed nanoparticles for enzymatic bioelectrochemistry. I have to say sorry because in the building there's some maintenance work and that be a little bit noisy from the background, but I hope they'll be okay. The outline today on my talk is about, firstly, I would like to briefly introduce you enzymatic bioelectrochemistry in case you are not in the field. And then I will introduce the material called Dealloyed nanoparticles, which I have been working on for more than 7 years, I think. And in the very end, I will introduce our recent work on fructose tRNAs. So for bioelectrochemistry or enzymatic bioelectrochemistry, we use enzymes, especially oxidoreductase on a solid surface. Typically, these enzymes, if you can see my cursor, typically those enzymes, it has a redox center. For example, like this enzyme shown here is a blue copper enzyme. The copper atom in the enzyme, it could electron transfer with a solid electrode. We call it direct electron transfer. This is in the case if the redox center is close enough to the electrode, then you can record some direct electron transfer based electrochemistry. And the Macros theory will work in this case. And tunneling distance, which means typically very important. It means we have to orientate the enzyme in a correct position to make it closer to the electrode, to make the electron is possible to tunneling. In another case, this is glucose oxidase, which has a cofactor called the FAD. Typically, this FAD is deeply buried in the enzyme, and it's impossible to get the electron to tunnel directly to the electrode. Then we have to use a small redox molecular, we call it mediator, to help shuttle the electrons from the enzyme to the electrode. Then we call it a mediated electron transfer way. In this case, the enzyme orientation doesn't seem to be an important issue, but we have to somehow tune the mediator redox potential to make it work in a proper way. This really depends on what kind of application you want to use. For example, if we are working on a glucose biosensor, we want the redox potential somehow higher. Then according to the Macros theory, we have much larger mediator introduced over potential over the redox potential of FAD, then we can get relatively much higher currents. Well, for biofuel cells, we want somehow decrease the over potential. Then we have somehow to make the redox potential or the mediator close to the FAD. For bioelectrochemistry, typically there are some applications. Firstly, it's a classic biosensor, which the enzyme catalytic, the oxidation or the reduction of the analyte, then we record the signal. This is a typical working principle for glucose biosensors, which we mobilize, for example, a glucose oxidase here. Another application is the bioelectrosynthesis. This is somehow turning to be a hot topic now. And for example, there's a possible way to convert some ketone into alcohol. So the conversion of some raw material to some high valuable products turn to be interesting. For example, recently CO2 reduction, and this can, and nitrogen fixation, those can all done by electrochemistry if we just screen the proper enzyme and do the bioelectrochemistry here. For my PhD, I'm more interested in biofuel cell, which is based on 2 electrodes. One electrode could do, for example, oxygen reduction, and the other way, on the bioanode side, we could do some biofuel oxidation. And then we can convert the chemical energy stored in the biofuel into some electricity. This will be very useful for some wearable medical device powers. Inspired by the talk last week about redox battery or redox flow battery, I found that enzymatic biofuel cell is somehow work similar to the redox battery. For the biofuel cell, if we use redox mediators, we have somehow, as I mentioned, we have to tune the redox potential for the mediators used on the anode side and the cathode side. Then we can push the measured open circuit voltage larger, because we typically want biofuel cell with a larger OCV. This is somehow similar to the methodology in redox flow battery or redox battery, which you are also tuning the redox potential of these small moleculars used in the redox battery. So then I found there was a very interesting work by Pore from Shalimintier's research group reporting enzymatic redox flow battery. The principle is that on the analyte, they were using NAD plus or NADH couple. This is the cofactor for NAD-dependent glucose dehydrogenase. And on the let's say catalyte, that's a ferricin redox couple is used. And when coupled with enzymes, for example, doing glucose oxidation on the anode side and oxygen reduction on the cathode side, they could demonstrate such a concept. Firstly, it is a redox battery. It could do charging and discharging, and charging and discharging for 2 cycles, and then it could function like an enzymatic biofuel cell. It could convert the glucose and oxygen into some electricity, and it could do discharging. This is just for your interest, which I think is, you can refer to the reference here to give a more clear idea. In the second part, I would like to introduce the material, the electrode material I have been using called Dealloyed Nanoporous gold. This material is typically obtained from gold-based alloy. We generally use a gold-silver alloy because gold and silver can forming alloy in any ratio. And then we do a chemical etching of the silver away, and with the dissolving of the silver and the remaining gold atom will reforming on the surface, and automatically it will form some porous structure. As you can see from the SEM and the TM image, the pores are randomly distributed, and they are continuous pores. Also, interesting study here is, if you can see from the STM, high resolution STM here, on the surface, there are some steps, and they found some gold 100 and the gold 111 surface. It means on the pores, there's some single crystal surface. This is confirmed by the electrochemistry study. Sorry. If we do the cyclic voltammetry of the gold electrode in sulfuric acid, we could see the fingerprinted oxidation peak and the reduction peak. Here on the CV on the left hand, it shows the CV of some single crystal surface. It shows different oxidation peaks, and all these peaks for gold 100, 110, and 111 can be found on nanoporous gold. So here it shows that nanoporous gold, it has some single crystalline feature, which we think this is interesting. If we compare the method to get porous gold material, there are typically several methods. For example, template methods on using a soft template of a hydrogen bubble to make a porous structure. And also there's another way, directly anodize pure gold into some rough surface. If we compare the advantage of Dealloyed methods, is we can get some bi-continuous pore structure, and the pore size typically in the range of 5 to 700 nanometer. And this is a relatively simple method. We only need to do is some chemical etching of the precursors. For my study, we have different gold, silver precursors. The first precursor is called gold leaf, which is commercially available. Typically, you can buy a 9K or 12K gold leaf. This is a gold-silver alloy. And then we can cut several pieces and make it float on a concentrated nitric acid. This gold leaf, it has a rough thickness of 100 nanometer. It's very thin, that's why it could float. It could float on the liquid. And at a certain temperature and the duration, we can turn this alloy into brownish porous gold. Then we transfer this film into a small substrate. Typically we use Xinxin electrode. Then we can do some electrochemistry here. The structure of this type of nanoporous gold is typically uniform with a randomly distributed pores. The second precursor we use is some spirited gold-silver precursor. The advantage of this method is that we can tune the gold-silver ratio and the thickness as we want. This methodology, I think, initially originated from Mihal's paper here, which is performed by Mihal when he was a postdoc in Edmund's research group. The data I showed is from my previous colleague, Theo. He shows that by tuning the Dealloyed conditions, such as the duration, temperature, the roughness factor, which means the real surface area over the geometric one, the roughness factor and the pore size could be tuned. Typically, the roughness factor will decrease with the increase in the pore size. This method could obtain a nanoporous gold film up to at least 1,000 nanometer. After dealloying, the film wouldn't crack. If over the limit, the nanoporous gold, it will somehow collapse will shrink due to the massive volume loss. But this nanoporous gold film, it is effective to be 1,000 nanometer thickness. So this method allows us to play with some parameters like pore size and the roughness factor. Then Theo can show that nanoporous gold for bioelectrochemistry study, for example, butyrene oxidase is a blue copper enzyme which could reduce oxygen. And the nanoporous gold, it somehow increase the operational stability of this enzyme over that on planar gold. And also a previous PhD, Ula in the group, she shows that for the osmium polymer-based biofuel cell, enzymatic biofuel cell, on nanoporous gold, it could resist much higher power density over a planar gold. Those show some interesting advantage of using nanoporous gold. And then I would like to show you some morphology effect of nanoporous gold or pore size effect. The first example is cytochrome C. Cytochrome C is not an enzyme, it's a redox protein, typically with a small size, around 7 nanometer. It has a heme group here. If we immobilize the cytochrome C on a gold electrode, we could obtain the redox behavior of the heme. And then Theo shows that there's a clear pore size effect. When the pore size is around 10 nanometer, which is somehow a little bit larger than the size of the enzyme, the redox protein, it gives the highest redox signal. Well, when the process is too big, which means a smaller surface area, then the signal also decreases. But when the pore size is too small, when the process is smaller than the redox protein itself, the response is also smaller. So here we see a clear pore size for the electrochemistry of cytochrome C here. Second example is butyrene oxidase. As I mentioned you before, this enzyme could do oxygen reduction. For the oxygen reduction response, Theo also found that in a pore size around 20 nanometer, which is when the size is above the size of butyrene oxidase, it gives the best ORR oxygen reduction catalytic response. which I think also interesting. For my PhD, I expand the second precursor further, that I try to spark the gold silver precursor on a plastic film, make it into a flexible nanoporous gold. And I developed a electrochemical etching method which don't use nitric acid, only use some neutral salt, which can do this Dealloyed method. This is based on anodization of the silver and then forming some pore structure. And this nanoporous gold is somehow bendable. It could bend up to 60 degrees, and without a great change on the sheet resistance. Then it can feature some practical applications. For example, that's one example of using the substrate to immobilize lactate oxidase and butyrene oxidase, and in between our two commercial contact lengths. And then we demonstrate that we can generate some power from the tier lactate, and it could generate some power in 5 hours. Here is just a demonstration. Further demonstration is that when we fabricate also a flexible solid electrolyte, we use a polymer called polyvalent alcohol. Here it could also preserve some water and glucose. Then we could demonstrate a flexible biofuel cell here. To summarize here is that we could fabricate nanoporous gold film and immobilize some redox enzyme there, and we could do some electrochemistry. Then in the second, in the very final part of the presentation, I would like to introduce you our recent work on fructose dehydrogenase. The experimental work is mainly done by the PhD student I supervise, Xiaomei. Xiaomei was previously the PhD student of Professor Jinong Zhang, and Jinong is also my postdoc supervisor, but she sadly passed away this year due to cancer. And Professor Jens Woodstrup, he's also involved in this work. Firstly, I'd like to give you some details of this enzyme. This fructose dehydrogenase is a membrane-bound enzyme. So it typically has 3 subunits, and on this subunit that embeds to the membrane, it has 3 heme. So for the structure here on the surface around the heme subunit, there would be some hydrophobic surface. It also has a FAD-based subunit, which could do the oxidation of fructose. And the electrons will then transfer to, we call it heme3 and heme2, with relatively low redox potential. And then the electrons can transfer from heme2 to the electrodes. This will allow fructose dehydrogenase is capable to do direct electron transfer. Well, according to literature, heme1 with a very high redox potential, it wouldn't be involved in the DT transfer. If we use a redox mediator, here is ferricin methanol, whose redox potential is even larger. And then we think it could undergo mediated electron transfer. The electrons could directly transfer from the FAD center to the redox mediator, then to the electrode. The good thing, we want to study this enzyme also because it's commercially available, which means we can easily get it. And if there are any commercial application of this enzyme, it could be easily scale up. But its the crystalline structure is still unknown. Means it in the PDB bank we cannot really find it. The isoelectric point is around 6.6. So in a testing pH of 5.5, overall it gives you a positive charge. So as I said, when we want to immobilize the enzyme, we have to consider what the enzyme surface would be, and how to orientate the enzyme is very important. From what we can do is that we can form a self-assembled monolayer on the gold substrate. This is just a very simple process. We soak the gold electrode in a cell. The structure will be, it has a H sulfur bond there. It could spontaneously form a good sulfur bond and forming a monolayer or submonolayer. And then we can tune the functional group on the terminal. For example, we can choose some with amino group or COH group. And then we can somehow tune the orientation of a redox enzyme. For example, this is an enzyme, and if its surface is like the functional group of the sum, then it will show some preferred orientation. And then we can get the direct electron transfer between the redox center to the gold electrode surface. For our study, we also consider using a single crystal gold, gold 1,1. Typically, it gives a very smooth surface, as you can see from this STM image of the gold 1,1 is quite smooth surface in comparison to the polycrystalline gold, which is on the surface is still very rough and not crystalline smooth surface. In comparison to the nanoporous gold, it also shows a defined CV in sulfuric acid, and from the reduction peak, we can use some converter to calculate the real surface area or electrochemical addressable surface area of the gold electrode. And we can somehow work out the roughening factor for gold 1,1 is nearly 1. So means the gold 1,1 electrode is quite smooth. For the nanoporous gold, we are using a film of 100 nanometer, a pore size of 30 nanometer, which is a reasonable pore size according to TR's previous work. The roughening factor is around 7. So means the nanoporous gold, it has somehow 7 times larger than a single crystal gold. So for our research, in the very beginning, we use the gold 1,1 electrode, and with different sums of different terminal groups. As you can see here, the fructose tRNAs is just physically adsorbed on the electrode surface. If it's a bare surface, when adding the fructose, which is the solid line here, we don't really see any DT response. When the terminal is amino group, which means a positive charge surface, we can somehow get some signal, as you can see when we add in fructose. When the terminal group is the OH group, which means non-charged, but a slightly hydrophilic terminal, we can see a very clear catalytic response to fructose. If the terminal is a negative charged COO group, we can also get some catalytic response. If the terminal is just no charge and a hydrophobic surface, the response is smaller. It's much smaller. The curves below is when we add in the mediator ferrocyanide. For the mediated electron transfer, we can address using this equation here. It will directly shows how many enzyme, the total enzyme on the electrode. So imagine the fructose tRNAs, a lot of them, they are immobilized on the surface. Some of them, they are in a right proper orientation, then they can do DT, but some of them, they are not in the proper orientation, then they are not addressable to DET. But if we add in the mediator, if they are catalytic active, then we can address them. So if we compare directly from the DET current and MET current, the ratio here, it will directly show us how many active DET capable enzyme on the electrode. This data is summarized in figure F, as you can see here. For OH terminal group, it gives the best DET ratio. So means in this case, if we use the BME cell, we can get around 13% of FAD capable for DET, but the others, they are not capable for DET. They are just MET capable, which means they are catalytic active. So then we try to understand the data, why different electrodes surface will get different DET. Then we did structure homology modeling. As I said, the crystal structure of the FDH is not available, but we could subtract the fructose FAD subunit from glucose tRNAs and the heme unit from cell sulfate tRNAs. So they are from the same homology, and then we can put them together, docking them together, and then we get homology modeling of the FDH. And this done with the help of Sue from Australia. What we can see is that for the surface charge of the FDH, is that overall we see some blue colors, blue surface, which means positive charge. This is corresponding to either side the isoelectron point of the enzyme. The enzyme overall it will show some positive charge. That's why a COH terminal surface with negative charge surface will have a high loading of the enzyme due to the electrostatic interaction. That's why in that case, we get the highest MET. But it doesn't guarantee the best DET. This is because, This is because on the HEM2 here, its surrounding surface is a mixture, as we can say, of the blue color and the red color. It means close to HEM2, which communicate to the electrode with the electrons. The surface charge is quite complicated. So negative charge surface doesn't guarantee the HEM2 will get close to the surface. And we also consider the hydrophobic surface as shown in the figure B, which shows in orange and green colors. The near to HEM2 and HEM3, there are indeed some hydrophobic region. This is corresponding to the surface that embeds to the membrane. But again, the hydrophobic surface wouldn't guarantee very good HEM2C orientation. For our data, it's shown that a surface terminate with OH group, which means a non-charged but a little bit hydrophilic surface will prefer a better orientation of the enzyme. That's why we get a better DT. We further, on good 1-1, we vary the length of the monolayer by using the same terminal of OH. We vary the length of 2 carbon, 3 carbon, 6, and 9. As you can see, the catalytic response is decreased greatly with the length of the CH groups. And when the carbon is short, it gives the best DT ratio. We believe this is reasonable because for the short carbon chain, the electron tunneling distance is the shortest, then it gives the best catalytic response. Then further, we adapt the simulation, some mathematic simulation from originally from Armstrong, and recently greatly used by Kenji Kano's group. And in this model, they regard an enzyme molecular as a sphere, and then it has the closest or the shortest distance for the enzyme to do DET on the electrode, and also the maximum distance. There will be a delta D here. It means the variation of different orientations. If the enzyme oriented over than D max, then it has no direct electron transfer. This equation, it considers the orientation distribution of the enzyme. And the equation is originally derived from the Bartle-Warmer equation. It has 3 variables we can tune. One is the Kc multiplied with the DT surface, the DT capable enzyme coverage, and this is one variable. It reflects the catalytic constant of the enzyme, and also the DT capable enzyme concentration. The second variable is beta delta D. Delta D, as I said, is the variation of the enzyme distribution on the electrode. Second is Kc over Kmax. We can vary these three variables and then to fit a polarization curve. Then we can get these parameters. The data is summarized here. When we increase the CH group numbers, the surface coverage of direct electron transfer is decreased sharply, and the beta delta D it increase sharply, which means the DT capable enzyme on the short carbon surface is much larger, and also the variation for the proper orientation on short carbon is the smallest, means it had a smaller variation of the distance. All this data shows that a short carbon surface will be nice. But if we measure the overall enzyme loading using some spectral photometer method, if we measure the overall enzyme loading, which including the DET capable and not capable enzyme, the loading on different electrodes, that's not so big difference. So which means the DT ratio is the key factor here. We further immobilize the enzyme with the different terminal groups on nanoporous gold. The trend we can see is similar to that on gold 1,1. The interesting thing here is figure A on the bare electrode. We can also see the DT signal. Well, on the bare gold 1,1, we cannot really see the DT signal of the fructose tRNAs. The best linker we found is also OH terminal group, as shown in the figure B. But if compared to the data we got on gold 1,1 and the nanoporous gold, the DT ratio on the nanoporous gold is much larger, although that's still around 90% of the immobilized FDH is not DET capable. If we compare the MET current density on the nanoporous gold, is almost twice of that on gold 1,1, which means the nanoporous gold, it only somehow increases the enzyme loading by twice. This is somehow smaller than the roughening factor of the NPG of 7. The final test we do is the stability test, because for bioelectrochemistry, stability also something important. What we can say is that the fructose tRNA that adsorbed on the electrodes is quite stable, and it could operate over 7 days. And the half-life time of the electrodes on the nanoporous gold is much larger than the gold 1,1. To know the reason, we did compare the initial DET and MET with the final signals. We could see from figure C and figure D, after 7 days operation, we could see the MET signal is still more than half there. So which means the enzyme is still catalytic active, and there are not many detaching from the electrode. But for the DET's response on gold 1,1, that's very poor retaining of this DET signal. But we could still see the DET signal on nanoporous gold. So we can safely conclude that here on nanoporous gold, it could maintain the stability of the fructose tRNAs by maintaining the DT capable enzyme. So, so this will be my presentation. I would like to make some conclusions here that I hope I can convince you that nanoparticle, it shows some interesting factors for enzyme electrodes. Apparently, it increased the electrode specific area. For the case we use, our 100 nanometers thick, it could improve the surface area of 7-fold, although this is not a big number. The nanoparticle, it shows some single crystal surface, but we are not sure yet how this will directly impact on the bioelectrochemistry. What we can say is that the electrochemistry of some small redox molecules on nanoparticles is faster than that on panel. This may be an interesting input here. Of course, with a larger surface area, nanoparticles could improve the enzyme loading, but it doesn't really improve the loading by a very great factor. It's much less than the roughness factor of the electrode. Due to the 3D structure, somehow we believe on nanoparticles it could improve the possibility of the orientation of a DT capable enzyme. And finally, I showed you that on nanoparticles it could increase the operational stability of the enzyme. So for the future study, I'm still not very sure for nanoparticles. What I can say is that there are some opportunities. Nanoparticles, for bioelectrochemistry research, we believe it's a reasonable substrate, although gold is expensive, but for bioelectrochemistry, we don't use a large surface areas. What we could do is we could vary the film thickness then we could somehow increase the roughness factor. We could further increase the response or the performance of the nanoparticle-based bioelectrochemistry. Another chance is that we could vary the morphology of the nanoparticle. If we could fabricate some gold, silver, or gold alloy microspheres or tubes, then we do some Dealloyed. We could get different morphologies of nanoparticles, and for sure there will be some it could be interesting substrate for enzyme loading later. And then is the flow condition. In flow reactors, this could somehow increase the diffusion properties of nanoparticles. So in the very end, I would like to acknowledge my previous research team in Limerick and supervisor Professor Adam Magner, and the current team in DTU chemistry, and also the funding source. And in the very end, I have to say I'm currently seeking for a postdoc position worldwide or somewhere in Europe, because this year it turned to be very difficult to get funding. I applied for a starting grant, but I didn't really succeed. So with this, I would like to thank you for your kind of attention, and I would like to take the interesting questions for you.